Welcome to kinematics. Whether a car is braking to a halt or a stone is dropping off a cliff, a single set of mathematical tools governs exactly how they move. These tools sit at the absolute heart of classical mechanics. In your exam, they appear everywhere. You will need them for definitions in Paper 1, full structured calculations in Paper 2, and for determining the acceleration of gravity in your practical papers. Let's build them. Almost every mark you will ever lose on the foundations of kinematics traces back to fuzzy definitions. Let's lock them down in the exact wording the examiner wants. We divide the world into scalars, which have magnitude only, and vectors, which have both magnitude and a stated direction. Distance is your scalar path length. Displacement is your vector, the straight line distance moved in a stated direction. Speed is the rate of change of distance, while velocity is the rate of change of displacement. That makes velocity a vector. Never define it as speed in a given direction. Mathematically, it is the rate of change of displacement. The phrase rate of change of is exactly what the mark scheme requires. Similarly, acceleration is the rate of change of velocity. Because velocity is a vector, an object accelerates if it changes speed or if it changes direction. A car driving at a steady speed in a circle is constantly accelerating. Pause here. If a sprinter runs 400 meters around a circular track and finishes exactly where they started, what is their total displacement and what is their average velocity? Because they return to the start, their straight line distance moved is 0. Therefore, displacement is 0, making average velocity 0 too. When an object moves in a straight line with a constant acceleration, we can describe its motion perfectly using 4 algebraic equations. We derive these from a velocity time graph. The single vital condition is that acceleration must be constant. On a velocity time graph, constant acceleration is a perfectly straight line. The gradient is the acceleration, and the area under this trapezium is the displacement. From the definition of acceleration, we get our first equation. Final velocity v equals initial velocity u plus acceleration times time. This is just the gradient formula rearranged. By finding the area of that trapezium and substituting our first equation into it, we get the displacement equation. S equals ut plus a half at squared. Notice the half. Dropping it is a very common exam error. Finally, if we eliminate time completely, we get v squared equals u squared plus 2as. You must memorize these, but remember their strict license condition. They only work if acceleration is constant. Every SUVAT problem gives you 3 known variables and asks for a 4th. Let's look at the method to solve them flawlessly. First, state your sign convention. Decide which direction is positive. Second, list out S, U, V, A, and T. Fill in your 3 knowns and put a question mark by the one you want. Finally, select the one equation that links your 4 variables and substitute. We take the forward direction as positive. List the variables. Initial velocity is positive 24, final is 0, and acceleration is minus 4.0 because it opposes the motion. We don't care about time, so we choose the time-independent equation. Substitute the numbers exactly as they are. Rearrange and solve. The stopping distance is 72 meters. When an object is thrown or dropped and air resistance is negligible, the only force acting on it is gravity. Because gravity provides a constant downward acceleration of 9.81 meters per second squared, the SUVAT equations apply perfectly. The mass of the object does not matter. The secret here is strict obedience to your sign convention. Let's set upwards as positive. The C is below the start, so displacement is negative 40. Initial velocity is positive 15, and gravity is negative 9.81. We need the displacement time equation. Substitute the values in. This forms a quadratic equation. Rearrange it to equal 0. Solve using the quadratic formula. We discard the negative time, giving 4.77 seconds. Notice how the maths handles the entire up and down arc automatically. You are required to know how to measure the acceleration of gravity experimentally.
The standard setup uses a steel ball bearing held by an electromagnet positioned a measured height above a trapdoor. When the power is cut, an electronic timer starts. When the ball hits the trapdoor, the timer stops. Because it drops from rest, the equation simplifies to height equals a half gt squared. If we plot height on the y-axis against time squared on the x-axis, we get a straight line through the origin. The gradient of this line is half of g. Pause and try this. If a student plots this graph and calculates the gradient to be 4.85, what is their experimental value for g? Because the gradient is half of g, we just multiply it by 2. The value is 9.70 meters per second squared.
That is kinematics. You can now define the core vector quantities, derive and apply the SUVAT equations, solve complex vertical motion problems, and analyze the practical experiment to measure g.